So this will be the video for the solution to question 5 on the 116 exam 1 in winter 21. And the key concepts in this particular question are understanding the position versus time for sort of expression for an object in simple harmonic motion, and also sort of connecting sort of there's two major concepts in the question that combines two, also thinking about the energy in a simple harmonic oscillator. So the top equation here looks at the position. If the object starts with x equals plus a at time equals 0, then its position is given as a cosine function, as a function of time. Then the energy in a simple harmonic oscillator, the total energy is equal to the maximum potential energy, assuming it's a block on a spring, which this question is related to, and that's also equal to k max. But this particular question will be looking more specifically at the potential energy, since the graph that's given in the question is a potential energy curve. So we have u max 1/2 k. This is a small error here. This should say a squared. So u at any time is 1/2 k x squared, but u max is 1/2 k a squared. So that's a small error there. Omega is also given as the root of k over m. That will also be applied to this question. So the two key reading sections are section 14.3 and 14.4. Okay, so they're the key ideas. Let's just introduce the question. So this is one of the versions for the question. So a 1.8 kilogram block on a frictionless surface is attached to a horizontal ideal spring. That's why we're dealing with that type of oscillator, a block attached to an ideal spring. The other end is attached to a wall. The block is moved 0.3 meters to the right of its equilibrium position and released from rest. So it means it's released from x equals plus a at time equals 0. So that then its position function is given as a cosine function. The block moves with simple harmonic motion, and we're given the potential energy. So again, we're combining two big ideas in chapter 14. So we're given the potential energy curve here. It should be parabolic, as is 1/2 k x squared. The potential energy is 1/2 k x squared, where x is the position. And what we're doing is asked to determine the position of the block at t equals 0.2 seconds. So if we think about the expression for the position, x of t is equal to a cosine omega t. We have some of these quantities, so we're trying to solve for x at t equals 20 seconds. So we have the time. We know that the positive amplitude is here is 0.30, so 0.3 meters. So we also have the amplitude. So what we don't have is omega. But as we sort of seen in the previous slide, this is our introduction slide, omega is the square root of k over m. And do we have enough information to solve for omega? Let's see. Do we have the we don't have the spring constant, but we do have the mass of the block. Okay. So that we don't have enough information exactly to solve for k. So what else do we know about the motion? About just given about the motion, we do have the potential energy, and we have the maximum energy. So we know that u max, so this is where I'll make the correction to the previous slide, is 1/2 k a squared. So in this particular expression, I can solve for k in terms of u max and a. So k in this example would be 2 times u max divided by a squared, and those are quantities that we do have. We can read the u max off of the graph here. It's 10 joules. And a squared, as I mentioned, is 0.3. So if we wanted to write an expression, write an expression for the position at 0.2 seconds, will be given as a times the cosine. Omega now is going to be the square root of 2 times u max. I'll bring the a squared down here, times the m that's in the original expression for omega, and this is times t, where t will be 0.2 seconds, and a will be 0.3 meters. So you can solve, in a sense, you can sort of solve for this sort of in stepwise form too, of course. If you wanted to first solve for the spring constant, then solve for omega, then plug the omega in, multiply it, multiply the omega times t, find the cosine of that product, and then multiply by a would be the sort of individual steps that you might make. And that's what I want to do algebraically here. I need omega, but I don't have k. I'm solving k in terms of u max and a squared, plugging that back into the expression for omega. We have the mass of the block, and we have so this last expression down here, we have all of these quantities. We have u max, we have the time, we have a, we have m, we have the a, so we do have enough information to solve for. And the version that had the 10 joules, the x was negative 0.18 meters, and the version that had 20 joules as u max, the x worked out to be negative 0.21 meters. Okay, so yeah, so it's a challenging question since it's combining both sort of the position of an object in simple harmonic motion with also sort of content on the energy of a simple harmonic oscillator, and thinking about, particularly in this example, of the energy of a system of a block oscillating on an ideal spring. Okay, yeah, I'll wrap the video up there, and follow up the videos for question 6.